the recording here. Okay, so we talked last Wednesday's class about derivatives and shapes of curves. We are learning how to use calculus to help us graph functions and understand the behavior of functions, as opposed to just looking at a graph. Basically what we're doing is we are going to use calculus to determine where the function is increasing and decreasing and where it's concave up, concave down. And then by computing a few simple points on the important points on the graph and using what we learned from our calculus analysis, we can graph that function very easily. And we don't need to rely on a calculator to graph the function. But it's also just important that you're understanding the behavior of the function. So that's what calculus does for us. And like I had mentioned on exam 3, I'm going to want you to use calculus to justify everything. Okay, naturally, and including the problems where you have to sketch a curve, or section 4.3, 4.2. I mean, you understand that. This is calculus, okay? Okay, so on that note, let you copy this example down. We did a polynomial the last time. We analyzed a polynomial using calculus, and now we're going to look at a rational function. So let me give you a moment to copy this down. Okay, so here we have this rational function, y equals x squared divided by x squared plus 3. We want to discuss the curve with respect to concavity, points of inflection, and local maxima and minima. And then we want to use the information to sketch the curve. Okay, one moment. Be right there. Okay, so how many remember rational functions from their pre-calculus, working with rational functions? Okay, Lynn remembers it, and Ian, you know, and Nicholas, good. You had the vertical asymptotes, and then, you know, maybe there's vertical asymptotes. You might have horizontal asymptotes. John remembers it. And how many found them, these are a little scarier, in a sense, than like polynomials? How many felt they were a little scarier? I mean, maybe scary isn't the right word, but how many of you felt a little more uncomfortable with the rational functions, their graphs and behavior, as opposed to polynomials? Okay, Nicholas says a bit. John says, okay. Well, and Lynn certainly says that. Let me just, okay, so calculus, though, will make you comfortable, much more comfortable with rational functions if we use calculus to graph this curve, to sketch the curve. So what's the first thing normally we look for, you know, when we use calculus to help us understand the behavior of a curve? That's right, Lynn, the derivative. So we're going to look at the first derivative. And what will the first derivative help us with? What's the first derivative going to help us with this function? Okay, good, Joe, good, C, Trevor, good, Ian. Critical numbers and where the function's increasing or decreasing. So let's go ahead to the solution here. So, okay, now the first thing I'm going to just note is that the domain of this rational function is from negative infinity to infinity. The denominator x squared plus 3 will never equal 0. Okay, and so of course what we have to do is take the derivative, and I'm going to take the derivative of this rational function using what rule? What rule? This is a rational function here. What rule do we need to use to take the derivative? What's the rule called? Quotient rule. Good, Zoe. Good, Lynn. So, okay, I do the quotient rule. Okay, I do the quotient rule here. And of course, I want to try to simplify, you know, so I have my first derivative here. Here's my first derivative, but I'm not going to, I can't really figure out where the function increases, decreases, or what the critical points are until of the function, unless I get that derivative in a simplified form. Okay, so of course, that's what I do here. I'm going to, you know, distribute the 2x here and here. Okay, and so it turns out then that after I combine like terms in the numerator, that f prime of x, the first derivative, is equal to 6x over x squared plus 3 squared, quantity squared. Okay. So now what do we do next? We have our first derivative. What's next then? If we're using calculus to analyze our function, make it equal to, okay, so of course that's good. Setting the first derivative equal to 0 will then help us find critical numbers. Okay, but also what I'm going to do, I also want to know where the function's increasing or decreasing. So I'm going to go right away to making a chart. I'm going to make a chart here, and then I get both answers. Okay, so what I do is there are 3 factors here. Well, I want to be careful. The derivative is in factored form, but there are 3 components to the derivative, to the first derivative. We have the 6, we have the x, and we have the x squared plus 3 squared. 3 components. So now we know that when x equals 0, the first derivative, well, I'm not even there yet. I'm not even there yet. What I'm going to, well, all right, I guess I do have to, along my axis here that I have at the bottom, this is the entire x-axis. Remember, the domain is from negative infinity to infinity. But I know x equals 0 is an important value because that's going to, why is x equals 0 an important value? Why do I include that? Why do I include x equals 0 on the chart? I mean, why do I have that value on the chart? Well, okay, but there must be a reason I put 0 there. I mean, why didn't I put like 5 on the chart? I mean, I'm talking about the axis here at the bottom. Well, look at your first derivative here. You said that values of x, I mean, to find critical numbers, critical numbers are where the first derivative equals what? Critical numbers are values of x that make the first derivative equal to 0. And what value of x is going to make that first derivative? That's right, Nicholas. Right, 0. So I know 0 is an important value. Okay, so I include that on the chart. And now what I do is I look at each factor. So like, for instance, 6, well, that's always positive. So remember, the first derivative equals 6 times x squared plus 3 squared. So 6 is always positive for any x value. X, though, will be positive when x is greater than 0, but x would be negative when x is less than 0. Right? So in my chart, I have minuses and pluses. And of course, x is 0 when x equals 0. X squared plus 3 squared is always positive. I have an error here, actually. There is one error in the chart. This should be a plus here, not a 0. No, Ian. Because remember, x squared, if x equals negative root 3 quantity squared is 3. So, yeah, well, that's okay. That's all right. That's fine. We're always learning. Okay, so so the x squared plus 3 squared factor is always positive. And so now, are there any questions so far? Are there any questions so far? Okay. Okay. Well, now, we do all this because we need to determine. Very good. Very good. Thank you, Calvin. Thank you, Lynn. I want to know where this first derivative is positive and where it's negative, because that'll tell me where the function increases and decreases. So, well, here, when it appears when x is less than 0, the first derivative is negative. Oh, how did we get that? How do we get that? How do we get that? How do we establish that when x is less than 0, the first derivative is negative for all x values less than 0? Good, Lynn. Positive times a positive times a, or positive times a negative times a positive. Right, from right here. Positive times a negative times a positive. Easy, right? Easy. That's easy. I like easy when I do things. On the other hand, when x is greater than 0, the first derivative is positive, and that's because why? Why is that? Why, when x is greater than 0, is the first derivative positive? It's simple, but that's right, Choco. That's right, James. That's right, Nicholas. Positive times a positive times a positive. Well, and actually, I want to be careful. Really, what you're doing is a positive times a positive divided by positive, right? And then over here, on this side here, you have a positive times a negative divided by a positive. Okay, we want to try to be precise. Okay, and so now, since the first derivative is negative, okay, since the first derivative is negative, okay, when x is less than 0, that means that our function is decreasing on negative infinity 0, on that interval. Since the first derivative is positive, when x is greater than 0, that means our function has to be increasing on 0 to infinity. Notice also that the first derivative switches signs from negative to positive at x equals 0. Right? The first derivative switches signs. So that means then there, since the first derivative is negative, well, no, actually, we can say this. Since the function's decreasing on negative infinity to 0, but then it increases on 0 to infinity, that means that f of 0 equals 0 is a local minima. So the chart will give you everything. And I will be looking for these charts on exam, on your third exam. Okay, now for the third exam, you're doing the problem or problems you're going to have are going to be polynomials because you've only worked with polynomials so far. But still, we talked about how to make charts. So I really look at the charts too. Things can get somewhat a little bit complicated. Well, what I'm trying to say is we want to make things as simple as possible, and the charts make things simple. Okay, I mean, really what we're doing here, a rational function is a relatively complicated function compared to like what you're used to, parabolas and cubic functions and trig functions. A rational function's a little more complex, but let's make our analysis simple. Okay, so now what's next? We know where our function's decreasing, we know where it's increasing, but there's a lot of ways a function can decrease, a lot of ways a function can increase. What do we need to know more about this function in order to graph it accurately? Kelvin says the second derivative. Okay, and that's because we got to look for concavity. We got to look at concavity. So here's what we do. Very good. We'll go. Well, are we okay? May I go to the next page? All right, very good. Well, let's head on over. So now the second derivative, well, I know what the first derivative is. F prime of x was equal to 6x over the quantity x squared plus 3 squared. And so again, I'm going to use the quotient rule. to take the derivative. And you can see we're using the quotient rule and the chain rule. You know, we're really using your derivative rules. Okay, so you have to be a little bit careful. I mean, this taking the finding the second derivative for this function is harder than finding the second derivative for a polynomial, right? But if we're careful, we'll be fine. So I use the quotient rule and the chain rule, and I get to this step here. And again, the name of the game is to simplify your derivatives. So, you know, I'm working on the numerator a little bit here. Working on the numerator. And, okay, well, so let's just, let me see here. Okay, so is there a common factor between the two terms? I mean, I'm looking, so remember, getting the second derivative in simplified factored form is the key. So I got two terms. Okay, x squared plus 3 is in common, and actually 6 is in common too. So I'll factor 6 times x squared plus 3. And so the numerator is going to be 6 times x squared plus 3 times x squared plus 3. You know, that's right, x squared plus 3, right, minus 4x squared. But that second factor, x squared plus 3 minus 4x squared, simplifies into 3 minus 3x squared. So we get down to here. Notice also that you know, we understand that we have 6 times x squared plus 3. Well, we have an x squared plus 3 factor in the numerator, and we have an x squared plus 3 to the fourth factor in the denominator. What can we do with the exponents? What can we do? What can we do with those? What can we do with the x squared plus 3s? Can we reduce? That's right. We can divide and reduce. So if we reduce, we'll get x squared plus 3 cubed here in the denominator. So it just takes a little bit of patience and a little bit of faith sometimes, but things do, you know, work out. Now things can get more complicated, right? And that's where sometimes, well, for session 4.3, things are gonna work out nicely, and that's valuable, right? To do that. Now, okay, we're right here now. We're right here. Here's my second derivative. So my second derivative equals 6 times the quantity 3 minus 3x squared over x squared plus 3 cubed. Am I happy yet? Am I happy with my second derivative the way it is? Should I be content with that? No. Nicholas says no. Well, why not? Why not? Lynn doesn't think so either. You can factor more. That's right. That's right, Lynn. That's right. So you can factor more. So we can factor 3. Okay, we can factor a 3 out of the 3 minus 3x squared. So that'll become 3 times 1 minus x squared. But I can write 1 minus x squared. I can write that as negative 1 times x squared minus 1. Okay, I can do that. And so I get negative 18 times x squared minus 1 over the quantity x squared plus 3 cubed for my second derivative. Are we happy yet? Oh, Yaki says, how does 3 times 6 equals negative 18? Well, don't forget, Yaki, we have the negative 1 here also. Because 1 minus x squared, I'm writing as negative 1 times x squared minus 1. That's how we get the negative 18 here. Okay, are there any questions so far? Yaki, you're good? Well, I mean, you can. So you're wondering about the negative 18, right? So all right, hold on. So you're good down to this step here, right? Maybe give me a thumbs up if you're good down to that step. Okay. So 1 minus x squared, I'm going to write 1 minus x squared as negative 1 times x squared minus 1. And then what happens is the 6 times the 3 times that negative 1 give you the negative 18. And so the second derivative, okay, yeah, that's how. That's right. Well, you know, I'm more comfortable with x squared minus 1 than 1 minus x squared. And are we happy here? Are we happy with the second derivative, the way it's written? Or is there something more I can do? Okay, indeed. We can break up the x squared minus 1. Okay, and let me just see here now. Good. Yeah, so this can be factored. This can be factored here. And we want to factor it. We want to factor it for sure. So, all right, let me go ahead to the next page, if I may. Okay, let me go to the next page. So now we have it factored. Second derivative equals negative 18 times x plus 1 times x minus 1 times x squared plus 3 squared. And now it's time to make another table. Time to make another table. Okay, so the second derivative, this is as good as we're going to get, has 1, 2, 3 factors on top, and then you're dividing by this x squared plus 3 cubed on the bottom. So that means I'm going to write each of these components down. And it is clear that because in the numerator you have x plus 1 times x minus 1, it's clear that along the x-axis here at the bottom, I'm going to include -1. I'm going to include -1 and +1 as important values. And then I just make the chart. I make my chart. For all values of x, -18 is always negative. X plus 1 will be positive when x is greater than -1. But x minus x plus 1 will be negative when x is less than -1. And of course, we know that x plus 1 is 0 when x equals -1. X minus 1 will be negative when x is less than 1. X minus 1 will be positive when x is greater than 1. And then finally, x squared plus 3 cubed is always positive, because x squared plus 3 for all x is positive. Okay, and so now, well, are there any questions so far? All right, well, now let's get to what we do this for. It's so we can determine where our second derivative is negative and where it's positive. So we determine, of course, that the second derivative is going to be negative when x is less than -1. And why is that? Why is that? Why is the second derivative negative here when x is less than -1? Well, I meant in terms of the chart. How are we getting a negative? Okay, I'm right. I'm seeing what Lynn's writing. She's saying a negative times a negative times a negative divided by positive. Very good. Very good. Well, Chaco, you're not multiplying everything. You got the you have the 3 factors on the top multiplied, but then you're dividing by the x squared plus 3 cubed. So these negatives here come from a negative times a negative, a negative times a negative times a negative divided by a positive. Okay, that's okay. And then when x is between -1 and 1, we have all positives. How do we get all positives? So I'm working with you on this so that I want to make sure that you're understanding and appreciating the charts. How do we get the positive there? How do we get when x is between -1 and 1? The chart tells us the second derivative is positive. Why is that? Based on the components of your second derivative, how are we getting a positive? Well, Nicholas, 2 negatives equals a positive, but could you be a little more like fundamental? Okay, this is what I mean. Then a negative times a positive times a negative. So a negative times a positive times a negative divided by a positive is positive. That's what I was looking for. Okay, I mean, I know that, Nicholas is thinking it right. And then finally, when x is greater than 1, okay, we have, it's positive, the second derivative is positive when x is greater than 1, because there we have a negative times a positive divided by a positive, and in other words, the -18 is positive, the x plus 1, sorry, the -18 is negative, the x plus 1 is positive there when x is greater than 1, x minus 1 is positive when x is greater than 1, and x squared plus 3 cubed is always positive, so hence, there you go. Okay, how many are finding these charts to be kind of cool? Yeah, Zoe likes them, and it just makes your life, because now Jocko likes them, John likes them, and look how much information we got. Yes, Nicholas, you have to do the charts for the exam. Yes, for section 4. The charts come up in section 4.3. Section 4.3. And there, for those problems from section 4.3, let me just see. Let me just check. Right, the charts come up in section 4.3. So any problem from section 4.3, I need to see charts for you to get proper credit. Okay, and likely full credit. All right, so now, good question, Nicholas, good question. All right, so now our function's concave down on -infinity to -1 because the second derivative was negative on that interval. So the second derivative is negative on the intervals -infinity to -1 and 1 to infinity. So that means our function is concave down. The second derivative is positive when x is between -1 and 1, and so f is concave up on that interval. Additionally, you have 2 inflection points. You have an inflection point at x equals -1 because the concavity switches from negative to positive there at x equals -1. And then you have an inflection point when x equals 1 because the concavity switches from positive to negative at that value of x. And so these are your 2 inflection points as I'm showing you here. So of course the inflection points, we evaluate function. So when x is -1, y is going to be a fourth. And also when x is +1, y is going to be a fourth. It shouldn't be surprising because this is a symmetric graph. It's the rational function x squared divided by x squared plus 3 is an even function, right? So it should be symmetric about the y-axis. So I'm not surprised about these inflection points. Are there any questions at all? Okay, Nicholas is good. Okay, and look at what we've learned now about this function. We've learned where the function, we've learned where the function is increasing. We've learned where the function's decreasing, you know, the x values for which the function's decreasing. We've learned where the function is concave up. We've learned where the function's concave down. We know where local maxima and minima are. Well, in this case, this function just has a local minima. And we have inflection points. So we've learned a lot about this function. We haven't used our graphing calculator at all, right? But now what we want to do is we want to put together, when we don't want to use our graphing calculator, right? We want to put all this information together to graph the function. And that's what I'm going to do on the next page. So may I go to the next page? Are we good? Are there any questions? Okay. Okay. All right. Very good. Very good. All right. And hopefully one of the students said they were going to be excited about today's class because they're learning all this cool stuff. So I hope that person's excited. Okay. Now I drew this function without a calculator. I drew our function. X squared over x squared plus 3 based on just the information that we have learned using calculus. So first of all, of course, I can plot these three simple points. The origin, we know the function goes through the origin. We know the function passes through the point, the coordinate 1/4, and the function passes through the coordinate -1/4. Okay, now what's the function doing? Look how I'm tracing this function. What's the function doing here? It is, well, we won't worry about the asymptote yet, Ian. We will get to that. But the way I'm drawing, it's decreasing. The function's decreasing. Okay, it's decreasing. And from, let's see, from -infinity to -1, the function's decreasing and it's concave what? Concave up. Okay, so CU here. Good. And then at -1, when x equals -1, the function continues to decrease until we reach 0. But what happened to the concavity? What happened to the concavity here? At x equals -1, oh, I have an error here. Hold on. This should be concave down, right? Okay, one moment. So what I'm saying is at x, when x equals -1, when x equals -1 at this point here, I mean, the function was decreasing, it was concave down. It continues to decrease, but now it's concave what? Now it's concave up. Good. Concave up. And then after 0, and again, all I did was I went back to, I went back to the information that I got based off my charts. Okay, the information I got based off the first and second derivative from my charts. And I used that information then to graph. Okay, so try to be neat about this. So here we're concave down. Where's the function appear to be concave up? Over what x values based on the picture? From -1 to 1. That's right. Right? And then from 1 to infinity, the function there is concave down. Now, in regards to the asymptotes, I have a little note here at the bottom. This is something you did in pre-calculus. There are horizontal asymptotes here, because if we look at the limit of our function, x squared over x squared plus 3 as x goes to infinity, well, that can be written as the limit as x goes to infinity by dividing by x squared in the numerator and denominator. That limit is going to be the limit as x goes to infinity of 1 divided by 1 plus 3x squared. Well, what does 3 over x squared go to? What does this go to as x gets large? What's that 3 over x squared have to go to? Has to go to 0. So you get 1. And so that's a horizontal asymptote on the right. So going to the right, there's a horizontal asymptote at y equals 1. But similarly, as x goes to negative infinity, we also get the same horizontal asymptote. So now we've graphed this rational function strictly using calculus and some, basic principles. Calculus makes it easy to understand, or easier to understand, the behavior of functions. So you can have rational functions which are considered more complex, but you can really, you can graph them quite easily using what you learned from your calculus analysis. Okay, are there any questions at all? All right, well, let me stop the